Hi, my name is Andrew Estornell. I'm going to be talking about the paper Election Control by Manipulating Issue Significance. This was co-authored by myself, Sanmay, Edith, Elkind, and Yevgeniy Vorobeychik. Now, if we're going to be talking about manipulating elections, let's first talk about elections in general and how we're going to model them. Elections will have a set of candidates and a set of voters. Voters will vote for a candidate, and the candidate with the most votes will win, meaning that we're looking at plurality elections. These candidates could be politicians, but they don't have to be. This election framework is extremely general and can capture a lot of different selection processes. For example, each candidate could represent a budget proposal, and maybe the voters are members of the school board trying to select which budget proposal they think is best for the school. Each candidate could also be a member of an online poll. For example, maybe there's a gossip website holding a poll for who the most influential celebrity of 2020 is, then the candidates are just the celebrities in this poll. Each candidate could also represent a movie that maybe you and your friends, the voters, are trying to select for movie night. Now, let's take a look at each candidate and voter and see how they're going to look in a little bit more of a mathematical sense. So the election will be over a set of issues. And for this example, let's just say that we're looking at something like a presidential election and that there are two issues. So the issues could be something like the candidate's charisma and energy, as well as the candidate's political ideology. Now, each candidate and voter is going to have an opinion on each issue. So here, the candidate has opinions -1, meaning that they're not particularly charismatic or energetic, and they have a political ideology that's to the left. The voter has opinions 1-0, meaning that they prefer candidates who are energetic and charismatic, and their political ideology is more to the center. As candidates and voters are both just vectors, we can embed them in two-dimensional space or in issue space in general. If we embed the candidate and the voter in this space and maybe add a few more candidates, we could measure the relative distance between the voter and each candidate. This distance represents how much the candidate and voter agree in general across all issues. So here, voter 1 and candidate 3 agree the most, meaning that voter 1 is going to vote for candidate 3. But like the title of the paper implies, issues have significance, and not each issue is going to be equally as important to a voter when selecting a candidate. In a presidential election, we would imagine that political ideology matters much more than charisma and energy. To account for this, we could think of expanding and contracting the different dimensions of this issue space. So here we saw that as we made political ideology more important, distances in the Y direction became more important, and distances in the X direction became less important. So now, even though that candidate 2 and voter 1 very much disagree on the first issue, they share the same political ideology, meaning that now candidate 2 and voter 1 are the closest in issue space, and voter 1 will now vote for candidate 2. Now that we've seen how we're going to model the significance of issues, let's next take a look at manipulating the significance of issues. One of the quintessential examples of the significance of issues being manipulated in the real world is that of Brexit. And we saw that even prior to 2015, Brexit was definitely part of British politics. It was just an issue of almost no importance. And from 2015 to 2016, we saw it quickly rise to being one of, if not the most important issues in British politics. And this was primarily the result of a multi-million-dollar ad campaign, which just attempted to bring Brexit to the forefront of voters' minds. And to model this manipulation of issue significance, we could imagine having an attacker here in red, and the attacker is able to alter how important issues are. More specifically, the attacker can't change anyone's opinion, meaning that they couldn't take a candidate or a voter and move them to a different place on the grid. However, they can expand or contract the dimensions of the grid like we saw before. So the attacker, maybe they want candidate 3 to win, so they could alter the significance of issues, making charisma and energy more important than political ideology, meaning that now voter 1 and C3 are closer than voter 1 and candidate 2. So here, V1 will now vote for candidate 3. Next, let's take a look at this in a little bit more of a mathematical notation sense. So we're going to have a set of candidates, a set of voters, each of which is just a vector in L dimensions, and L is going to be the number of issues. We will also have a weight vector that is going to represent how important each issue is, and this will again be L-dimensional. We will have the distance between candidate I and voter J, and this is just a weighted LP norm. We can see that it's a regular LP norm just with the weight folded in at each dimension, representing how important that particular kth issue is. The voters are going to pick the candidate that's closest to them. So here, voter J will just vote for the candidate that's the argmin of the distances. We also have an attacker who's going to have a budget, and the attacker has a desired candidate. Let's just say that it's candidate 1, and they're able to manipulate the significance of issues by altering W with the hope of making candidate 1 win. And they can manipulate W by proposing a new importance vector, W prime, and they're just restricted such that W prime can't be too far from W in LP space. So we can propose a new importance vector. It just can't be too far from the original significance of issues. Now let's look at complexity. And although this is a continuous optimization problem, it ends up being the case that it's NP hard, even for 2 candidates, binary issues, and an unlimited budget. And the reason that this is hard is that the problem boils down to a combinatorial selection problem. We're essentially trying to determine which subset of voters to make vote for our desired candidate. So even though W itself is continuous, we still end up having this kind of binary selection process. However, there is kind of light at the end of the tunnel because there's an easy part of this problem, which is that for any subset of voters, it's easy to determine if they can all be made to unanimously vote for our candidate. And the intuition behind this is it can just be framed as a convex feasibility problem. We can use the fact that it's easy to check if a subset of voters can be made to vote for our candidate to optimally manipulate the election. So if we were to just check every single subset, this would still be a combinatorial problem. However, in the paper, we provide a wide range of instances of problems such that only a polynomial number of these voter subsets would have to be searched in order for you to determine if your desired candidate could be made to win the election. We also study several different extensions to our model. So before we saw that voters vote deterministically in the original example. However, we study a case where voters vote stochastically based on how far they are from each candidate. We also study different objectives for the attackers, such as maximizing the number of votes for a desired candidate, rather than just determining if the candidate can or cannot be made to win an election. And we also study different restrictions on the attackers. So rather than just having some budget and an LP norm, we also study different restrictions on the attacker's strengths. So in conclusion, we saw that manipulating elections in general is NP hard. However, determining if a subset of voters can be made to unanimously vote for a desired candidate is easy, and this can be used to optimally manipulate elections in a wide array of cases. And we also saw that we get similar results for further extensions to our model. Thank you very much, and I encourage you to please go and check out the paper.